Let's work with some double angle identities. Given that cosine theta is 3/5 and sine of theta is less than 0, find the sine of 2 theta, the cosine of 2 theta, and the tangent 2 theta. To begin with, given cosine theta is 3/5, we need to find the sine of theta, the numerical value for it. Using the Pythagorean identity, cosine squared plus sine squared equals 1. For cosine, I'm going to put 3/5. So I have 3/5 squared plus sine squared equals 1. 3/5 squared is 9/25 plus sine squared theta equals 1. Now I'm going to solve for sine squared by subtracting 9/25 from 1. 1 is the same as 25/25. 25 minus 9 is 16/25. Now at this point I'm going to take square roots of both sides, and I have to think this through. Sine of theta is both positive and negative the square root of 16/25, which is 4/5. But I'm told that the sine of theta is less than 0, so I'm going to keep negative 4/5. Sine of theta is negative 4/5. Now based on this and cosine theta, I'm ready to find and use the double angle identities. Let's start with sine 2 theta. I know that cosine theta is 3/5, sine of theta is negative 4/5. The double angle identity for sine of 2 theta is 2 sine theta cosine theta. Put in values for those, which is 2 times negative 4/5 times 3/5, and we multiply. I have 2 times negative 4, which is negative 8, times 3, which is negative 24, over 25. The sine of 2 theta is negative 24/25. Let's continue. We also want to find the cosine of 2 theta. Given cosine theta is 3/5, sine theta is negative 4/5. Well, there's 3 versions of the cosine double angle identity. Let's use cosine squared theta minus sine squared theta and put in the values that we know. We'll put in 3/5 for cosine and square that. We'll put in negative 4/5 for sine and square that. Squaring 3/5, I get 9/25. Squaring negative 4/5, I get 16/25, and now I need to subtract. 9 minus 16 is negative 7/25, and that's the cosine of 2 theta. Let's do one more part here. Let's find the tangent of 2 theta. Now the tangent double angle identity is that we take 2 tangent of theta and divide it by 1 minus tangent squared of theta. But I have cosine and sine, so we need to take a minute to find tangent of theta by taking sine and dividing it by cosine. When we divide those, if we multiply by the reciprocal of the denominator, we end up with negative 4/3. And so there's a value that I can use for tangent theta to find the tangent of 2 theta. It's 2 times negative 4/3 over 1 minus negative 4/3 squared, and I need to simplify. This is negative 8/3 over 1 minus 16/9. Cleaning up the denominator, that's negative 8/3 divided by 9/9 minus 16/9, which is negative 7/9. If I multiply by the reciprocal, I need to find negative 8/3 times negative 9/7. I can simplify a factor of 3, and this is 24/7. So the tangent of 2 theta is 24/7. Let's work with some trig identities. We want to find the values of the 6 trig functions of theta if cosine 2 theta is 4/5 and theta is between 90 and 180. Well, we know some things about cosine 2 theta. One thing we know is that cosine 2 theta is 1 minus 2 sine squared of theta. If cosine 2 theta is 4/5, I can put that for cosine 2 theta, and I can solve this for sine of theta. Well, let's do that. I'm going to subtract 1, which is 5/5, from 4/5 will leave me negative 1/5 is negative 2 sine squared of theta. I'll divide by -2 to get positive 1/10 is sine squared of theta. Now I need to take the square root of each side. If I do that, I get plus or minus the square root of 1/10 is sine theta, and I can simplify. Now if you look back on our problem description, we were told that theta was between 90 and 180, which is in quadrant 2. Sine's positive in quadrant 2, so I'm going to keep positive this square root. The square root of 1 is 1. There isn't an exact square root 10, so we could use for sine theta 1 over square root 10, or we could rationalize the denominator and call that the square root of 10 over 10. And I've got the sine of theta. Now I need all other 5 trig functions of theta. This is what I have so far. I know that theta is between 90 and 180. Sine of theta is 1 over square root 10, which is the same as square root 10 over 10. What I'm going to do before I get too much further is sketch an angle theta in quadrant 2. So here's my angle theta. And label sides so that the sine is 1 over the square root of 10. So here's a 1, here's square root 10. Now I need to find this other side of the triangle, and if you use the Pythagorean theorem, that comes out to 3, and I'm going to call it -3 because I am to the left of the y-axis, or in the negative x direction. Now based on that picture, I can see that the cosine of theta is -3 over the square root of 10. The tangent of theta is going to be 1 over -3, or -1/3. And I have the sine of theta here. I should actually rationalize the denominator for cosine, so I'll call this -3 square roots of 10 over 10. Now using reciprocal identities, the reciprocal of the sine is the cosecant. The cosecant theta is going to be the square root of 10 over 1. The reciprocal of cosine is the secant, so the secant of theta is going to be negative the square root of 10 over 3. The reciprocal of tangent is the cotangent. The cotangent of theta is going to be -3 over 1, or just -3. Let's verify an identity. We want to verify cotangent x times sine 2x is 1 plus cosine 2x. I'm going to work on the left-hand side, and for cotangent, I'm going to put cosine x over sine x. For sine 2x, using the sine double angle identity, 2 sine x cosine x. Now this is multiplication, and I see that I have sine over sine, so I'm going to simplify those and multiply what's left to give me 2 cosine squared of x. Now there's a cosine double angle identity. Let me write it down over here. The cosine double angle identity is cosine twice some angle is 2 cosine squared of that minus 1. Well, I have 2 cosine squared of some angle, and I'm trying to conclude that it is 1 plus cosine 2x. Notice that if I took this one and added it to the left-hand side, I would have a statement that says 2 cosine squared of a is cosine 2a plus 1. So I can conclude that what I have is 1 plus cosine 2x, and I verified that identity. Let's work with some double angle identities. We want to simplify cosine squared of 7x minus sine squared of 7x. We have this cosine double angle identity that says cosine of twice an angle is cosine squared of that minus sine squared of that same angle. Well, what I'm going to do in this identity is replace a with 7x, and the right-hand side will be cosine squared of 7x minus sine squared of 7x. If I replace a with 7x on the left, I end up with cosine of twice 7x. The left side simplifies to the cosine of 14x, and I've simplified my expression. Let's try another. We want to simplify sine of 15 times cosine of 15. Now I want to use the sine double angle identity. Sine 2a is 2 sine a cosine a. But I don't exactly, in my expression that I'm trying to simplify, have 2 sine a cosine a. I do have sine something cosine that same thing. So what I'm going to do to make my identity match the expression I'm trying to simplify is divide each side of the identity by 2. That'll simplify the 2's on the right and give me 1/2 sine 2a is sine a cosine a. And now if I replace a with 15 degrees, the right-hand side is sine of 15 cosine of 15 degrees. And that matches what I'm trying to simplify. So I'm going to put 15 degrees for a on the left-hand side, and I need to simplify 1/2 sine of 2 times 15 degrees, which is 1/2 the sine of 30 degrees. Now I need to put in the sine of 30 degrees, which is itself 1/2, so this ends up becoming 1/2 times 1/2, which simplifies to 1/4. Let's work with some identities. We want to write sine 3x in terms of sine x. So what we have is sine 3x, and I'm going to start by considering 3x to be 2x plus x and apply a sine sum identity. So this is going to be applying the sine sum identity, sine 2x cosine x plus cosine 2x sine x. And now I'm going to put in a sine double angle identity and a cosine double angle identity to get myself entirely in terms of sine, or get towards that goal. Sine 2x is 2 sine x cosine x, and I have that times this other cosine x. There's 3 versions of the cosine double angle identity, but I want to be in terms of sine x, so I'm going to use 1 minus 2 sine squared x, that particular version of the cosine double angle. Now cleaning up what I have 2 sine x times cosine squared x, plus distributing, I have sine x times 1 minus 2 sine times sine cubed of x. And I want to continue. I'm trying to get entirely in terms of sine, so for cosine squared, I'm going to put the Pythagorean identity, which is 1 minus sine squared of x, and I have that plus sine x minus 2 sine cubed of x. And now I'm going to distribute one more time, and let's work that on another sheet. If I distribute, I end up with 2 sine x minus, I'm going to end up with 2 sine x times negative sine squared, which will be negative 2 sine cubed of x. I have that plus sine x minus, let's look one more time, 2 sine cubed of x minus 2 sine cubed of x. Now combining like terms, I have 3 sine x minus 4 sine cubed of x, and I wrote sine of 3x, which is where I started, entirely in terms of sine x. Let's look at an application problem. If a toaster is plugged into a common household outlet, the wattage consumed is not constant. Instead, it varies at a high frequency according to the model W equals V squared over R, where V is the voltage and R is a constant that measures the resistance of the toaster in ohms. What we want to do is we want to graph the wattage W consumed by a typical toaster with R equal to 15 and V equal to 163 sine 120 pi t in the window 0.05 by negative 500 2000. And then we want to count how many oscillations there are in that window. Well, here's the wattage. Let me put in what we need to graph. We're going to put in 163 sine 120 pi t all squared divided by 15. Well, let's graph this on a calculator. We're going to go into y equals. We're going to use parentheses for the numerator. 163 sine 120 pi times x for the calculator. We can't use a t. Close for the numerator, square that, and divide by 15. Then we'll set a window. We've gone 0 to 0.05 in the x direction with a scale of 0.01. Negative 500 to 2,000 in the y direction with a scale of 500. And we'll take a look at the graph. And what we see is a graph of the wattage, which is the voltage squared divided by the resistance. And the other question we wanted to answer was how many oscillations there are. And if you count the number of peaks that you're looking at here, you can see there are 6. What we're looking at is a part of the graph that contains 6 oscillations. Let's use a product to sum identity. We want to write 4 cosine 75 degrees times sine 25 degrees as a sum or difference of two functions. Well, this is a cosine times a sine. The cosine times sine product to sum identity is that cosine A times sine B is 1/2 times the sine of A plus B minus the sine of A minus B. So I'm going to use this. For A, I'll use 75 degrees. For B, I'll use 25 degrees. And I'll multiply each side by 4. So if I want to find 4 cosine 75 degrees sine 25 degrees, I have to find 4 times 1/2 of the sine of 75 plus 25 degrees minus the sine of 75 minus, I'll write plus negative 25 degrees. That's a negative right there. Continuing, 4 times 1/2 is 2, and this is going to be the sine. 75 plus 25 is 100 degrees minus the sine of 75 minus 25, which is 50 degrees. And I'll stop at that point. Let's use a sum to product identity. We want to write sine 2 theta minus sine 4 theta as a product of two functions. So we want to use the identity sine A minus sine B is equal to 2 times the cosine of A plus B over 2 times the sine of A minus B over 2. We'll use for A 2 theta and for B 4 theta. So sine 2 theta minus sine 4 theta is 2 cosine of 2 theta plus 4 theta over 2 sine 2 theta minus 4 theta over 2, and we need to simplify. So 2 cosine 6 theta over 2 sine negative 2 theta over 2. Continuing, that's 2 cosine 3 theta sine negative theta. But sine of negative theta is negative sine theta. Pulling that negative out and bringing it to the left, this is negative 2 cosine 3 theta sine theta.